Hello, my name is Ivo Garas, and today I want to talk about my chosen topic. So, traditional AI models predict text one word at a time, right? But what if we could process entire concepts instead? Well, large concept models represent a shift in AI by focusing on a higher level of reasoning, improving efficiency, and enhancing understanding across languages and modality. In this presentation, I'm going to explore what makes LCMs different, their advantage over traditional large language models, and their potential impact on various industries. We've all seen that AI has advanced rapidly, with LLMs like ChatGPT excelling at text generation and summarization. However, they process text word by word, making it really hard to maintain coherence, handling long contexts, and scaling efficiently. LCMs take a different approach by processing entire concepts instead of individual tokens. As we see in the chart, LLMs follow linear tokenization and transformer-based pipeline, whereas LCMs use sentence segmentation, SONAR embeddings, diffusion-based reasoning, and quantization for more structured understanding and efficiency. Well, you might ask yourself, what are SONAR embeddings? Well, SONAR embeddings allow LCMs to grasp entire sentence meanings rather than just words, helping them recognize, for example, a physician helped someone recover is the same as the doctor treated the patient. Diffusion-based reasoning also refines outputs gradually. Similar to how an image is sharpened step by step, this allows LCMs to generate more coherent summaries, structured responses, and better multilingual understanding with less computational cost. LLMs are no longer the new kid on the block. By shifting from token-based to concept-based AI, LCMs offer a more efficient, scalable, and context-aware alternative to traditional LLMs. Now, let's look at a higher level overview. The chart illustrates how LCMs process information differently from traditional LLMs. So instead of handling word by word, we see that in the architecture, LCMs encode entire sentences into a term called concepts. It's using a fixed concept encoder. These kind of encoders are then processed by the LCM, which allows for higher level reasoning and better context retention. Finally, we see that the concept decoder converts these structured concepts back into words, enabling more coherent and efficient text generation. This is the approach which makes LCMs more scalable and context-aware and efficient than token-based models. So, why have I chosen this topic? Well, the topic is critical because LCMs address key limitations of LLMs. They offer better generalization and efficiency. The chart compares 2 Tower 7BIT in blue and Llama 3.18b. The blue is LCM and the red is an LLM. On text summarization across multiple languages using the XLUM Rogue L score, a key metric for evaluating output quality. A major takeaway from the paper is that LCM significantly outperform the 3.1, particularly in low resource languages like Vietnamese, Pashto, Swahili, and Burmese, despite never being explicitly trained on them. Unlike LLMs, which require fine-tuning for each language, LCMs generalize efficiently across unseen languages due to their concept-based processing. This result demonstrates the scalability and efficiency of LCMs, reducing the need for extensive multilingual training while maintaining high performance. This breakthrough opens new doors for more accessible multilingual AI applications with significantly lower computational costs and latency. Digging deeper, we see the chart compares inference flops, which means computational cost, across different context size. The blue line, which shows the non-LCM model, shows a steep exponential increase in flops as the context size grows. In contrast, the 2 tower models, which are both LCMs, maintain a much lower computational cost, providing that LCMs can handle larger context size efficiently without massive resource demands. This efficiency means LCMs can process long-form content more effectively, reduce infrastructure costs, and scale to real-world applications where LLMs would struggle with computation-heavy tasks. This unlocks a trove of new opportunities for real-time inference. Now, let's have a look at a human-readable example. The chart illustrates how LCMs structure reasoning by mapping concepts hierarchically rather than processing text sequentially like LLMs. The left path represents a step-by-step logical progression, where each concept builds on the previous one, maintaining coherence over large contexts. The right path shows an alternative reasoning route, demonstrating how LCMs can infer multiple possible conclusions rather than following a fixed sequence. The nodes and arrows depict how LCMs organize concepts at a different level of abstraction, ensuring more structured and flexible decision-making. Unlike token-based models that predict the next word in isolation, LCMs process entire ideas, allowing for more context-aware and adaptable reasoning, as shown by the branching structure. The visualization, it highlights the hierarchical and non-linear reasoning that sets LCMs apart from traditional LLMs. In the paper, The Future of AI, Exploring the Potential of Large Concept Models, Hussein Ahmed pointed out some pretty good applications for LCMs in the future. Firstly, let's talk about multilingual NLP. So traditional AI models struggle with translating and summarizing across multiple languages without extensive fine-tuning. as we've seen in the charts previous. However, LCMs operate in a language-agnostic embedding space, meaning they can process over 200 languages efficiently without needing to be retrained for each one. This is quite a game changer for businesses operating globally, allowing seamless cross-lingual content creation, real-time translation, and multilingual customer interactions. Next is cybersecurity. The paper highlighted that LCMs are particularly useful in enhancing threat intelligence. Unlike conventional models that rely on keyword detection, LCMs analyze entire security reports as structured concepts. This means that they can detect patterns in cyber attacks, analyze phishing attempts, and even automate responses with higher accuracy. So, for example, LCMs can process multiple threat reports simultaneously, identifying emerging risks faster than traditional AI models. In healthcare, medical records are often long, complex, and filled with unstructured data. LCMs solve this by summarizing patient histories, clinical trials, and medical research in concise, meaningful insights. Additionally, their multilingual capabilities make doctor-patient communication more accessible worldwide. So, a hospital using an LCM-powered system to generate easy-to-read summaries of patient medical history, reducing the burden on doctors while improving treatment decisions. And lastly, we have education. LCMs are revolutionizing adaptive learning. So unlike traditional AI tutors that rely on pre-programmed responses, LCMs dynamically adjust to a student's learning needs. They can provide a real-time feedback, summarize lessons, and even assist with multilingual accessibility, making education more inclusive. Picture an AI that understands the broader context of a student's essay and offers concept-based feedback rather than just correcting grammar. For the impact, LCMs enhance AI interactions by processing information at a conceptual level, improving multilingual and multimodal understanding for individuals. For businesses, LCMs leverage scalable AI solutions, reducing computational overhead while maintaining context-aware decisions. And at the societal level, LCMs contribute to more inclusive AI by mitigating language and modality constraints, optimizing for cross-lingual processing, and enabling more efficient data integration across global systems. So, in conclusion, LCMs represent a significant advancement in AI, improving structured representations and multimodal reasoning. Future directions include expanding their capability to additional modalities, integrating cross-domain embeddings for more robust context alignment. Refining hierarchical processing will enhance multi-scale abstraction, improving model efficiency and dynamic task adaptation. Another critical area is optimizing interpretability, a true explainable AI techniques, leveraging sparse attention mechanisms and modular architectures to reduce computational complexity while maintaining high performance. These improvements aim to enhance LCM scalability, efficiency, and real-world adaptability across diverse AI-driven domains. This presentation was done from the research by Ahmad and Goel 2025, which focused on practical implementations of LCM models, analyzing their capabilities across various domains. While meanwhile, Meta's 2024 work provided the foundational insight into LCM architecture and development. The accompanying technical resources, including the SONAR embedding GitHub and Meta's official LCM repository, offers deeper access to model structures, implementation details, and ongoing advancements in the field. Feel free to check out these resources because they're very interesting, and I feel this is only the beginning for the development of LCMs and LCM-related architecture. Thank you very much for listening to my presentation, and I hope you found it very insightful.